All right, y'all. So we're going to start off with good old Pythagorean theorem, and we have a right triangle. So remember Pythagorean theorem, we have a squared plus b squared equals c squared. And we can manipulate this equation to figure out any sides that we need as long as we have two, or that as long as we know two out of the three. So for example, if I was looking for side A, then I would simply subtract b from c and then square root both sides, and that would give me a. So that's if we're working with the right triangle. But the moment we add it into the coordinate plane and we talk about right triangles, we refer to them using our unit circle. And so that kind of changes what we label the sides. So because we're on a unit circle on a coordinate plane, the sides can be referred to, well, first of all, we have coordinates, and those coordinates are represented by trig functions. So x is represented by cosine theta, where theta is my angle of reference, and my y values, or my y coordinate, is represented by sine theta. And so we can think of this side A as sine theta, and we can think of side B as cosine theta. And our C, remember, this is a unit circle, has a unit of 1. And so if we kind of still apply the Pythagorean theorem, then we end up with the most important identity, in my opinion, is the Pythagorean identity, which is sine squared theta plus cosine squared theta is equal to 1, because all I did was replace what A and B were with my sine theta and my cosine theta. So why is this the most important identity? Well, from this one trig identity, we can figure out two others and then manipulate it however we need to get different identities as well. So for example, notice how on the first one I solved for side A to get A by itself, right? And so in similar fashion, if we take our Pythagorean identity and let's say we solve for sine theta squared, or sine squared theta, then I simply move or subtract cosine theta from both sides, and I end up with sine squared theta is equal to 1 minus cosine squared theta. And from that, starting over again, instead of solving for sine theta, if I wanted to solve for cosine theta, then I would end up with 1 minus sine squared theta, and so on and so forth. If I put a negative in front, then it changes everything again. And here's one of the cool things. So if we start off with sine squared theta plus cosine squared theta, and instead of subtracting, then we divide everything by sine squared theta. Divide that by sine squared theta, and then we simplify, then we get another trig identity, cosine squared theta, cosecant squared theta. And from that one other trig identity, I can also solve and manipulate however I want and give me even more identities, right? So for example, if I wanted to solve this one for cotan squared theta, then I would end up with cosecant squared theta minus 1, and so on and so forth, right? And so that's why it's important there. And one more. So if we start once again from sine squared theta plus cosine squared theta, and instead of dividing everything by sine, we now divide everything by cosine squared theta, Then, and we simplify, we end up with tan squared theta plus 1 is equal to secant squared theta, and we have another trig identity. And in similar fashion, if I wanted to solve for tan squared theta, then I simply subtract 1 from both sides, and I end up with secant squared theta minus 1, and vice versa. And so from that one right triangle and the unit circle, we were able to get 1, 2, 3 of the most common trig identities, and from those 3 we were able to produce or manipulate those particular equations for other identities, right? And so the 3 main ones that we focus or that we talk about are these 3 here, right? So this is kind of what we came up with, and the most important one is your original Pythagorean identity, because from that one we can produce the other 2.